Use the discriminant to predict the number and type of solutions the equation below should have. So to use the discriminant, we need to know that the discriminant is b squared minus 4ac. So I know that a equals 5, b equals negative 4, and c equals 3. So when I compute negative 4 squared minus 4 times a times c, I'm going to reach over for my calculator and type this all in. You should definitely be using your calculator on this, and make sure you put that negative 4 in parentheses. Negative 4 squared minus 4 times 5 times 3 is negative 44. So I have a negative discriminant, which means that I have radical negative 44 in the quadratic formula, so I have two complex solutions. And it's important to notice that these two complex solutions will be conjugates. They'll be conjugates of each other because the way the quadratic formula is set up. So number 2 says solve this equation. Does this match our prediction? Well, we know that x equals negative b, so 4, plus or minus the square root of the discriminant, all over 2a. 2 times 5 is 10. So those are the solutions. Now we need to simplify this. Radical negative 44. Well, first of all, there's a negative in my radicand, so I'm going to take out that I, take out that square root of negative 1 as I. 44 is 4 times 11, so that's 2i radical 11. So x equals 4 plus or minus 2i radical 11 all over 10. Distribute that 10, we get 4 over 10 plus or minus 2 radical 11 over 10i. You could switch the order. I like having that real number up front. 4 divided by 10 is 2/5 plus or minus radical 11 over 5i. Those are my two solutions. I predicted they'd be complex. They are. Are they conjugates? 2/5 plus radical 11 over 5i, 2/5 minus radical 11 over 5i. They are conjugates of each other. So when we solve quadratic equations that have a negative discriminant, their solutions will be complex. Solve the equation. It's a quadratic. Regardless of what we're doing when we solve quadratics, we set it equal to 0. 2x squared plus 8x plus 9 equals 0. Now you should check, can I factor this? And you're going to have to use the AC method. What multiplies to a times c? What multiplies to 18? That adds to 8. Do those numbers exist? 1 and 18? No. 2 and 9? No. 3 and 6? No. So it doesn't appear that there's any integers that'll solve this equation, that'll help me factor this, so I'm going to use the quad formula. A, B, C, b squared minus 4ac. A is 2, b is 8, c is 9. My discriminant is 8 squared minus 4 times 2 times 9. Reach over to your calculator and type that in. 8 squared minus 4 times 2 times 9. I got a discriminant of negative 8, which makes sense that I can't factor this because I have two complex solutions. You don't need to write that every time, but I have two complex conjugate solutions. Now I can use the quad formula. X equals negative 8, negative b, plus or minus the square root of the discriminant over 2a. 2 times 2 is 4. On the side here, I hate that negative, so that's I radical 8. Radical 8 is 4 times 2, so 2 radical 2. So I know x equals negative 8 plus or minus 2i radical 2, all over 4. Well, I can distribute that division by 4 and get x equals negative 8 over 4 plus or minus 2i radical 2 over 4. Negative 8 over 4 is 2, plus or minus negative 2, plus or minus 2 divided by 4 is a half, so radical 2 over 2i, if I use the commutative property there. Those are my solutions to this quadratic equation. Number 4, solve this equation. Again, it's a quadratic equation, so I should set it equal to 0. So I'm going to have to kick that x term over. 3x squared minus x plus 1 equals 0. Can I factor it? What multiplies to 3 times 1 that adds to negative 1? Nothing. So it can't be factored. Let's use the quad formula. A is 3. B is, well, negative 1 is in front of x, and C is positive 1. The signs come along when you pick out these coefficients. Let's compute the discriminant. Negative 1 squared minus 4 times 3 times 1. Negative 1 squared, make sure you square that right when you type that into your calculator. So that's 1 minus 4 times 3 times 1. So I have a discriminant of negative 11. Again, makes sense. I have complex solutions. My discriminant's negative. X equals negative b, 1, plus or minus the square root of the discriminant, over 2a, over 6. So x equals 1/6 plus or minus radical 11i over 6. Can't do anything with radical 11, so I'm going to leave my answer like that. Is it okay if you wrote I radical 11 over 6? It is, but this is in true a plus bi form. 5. Determine the value of k such that x squared plus 5x plus k equals 0 only has one solution. Well, if something only has one solution, the discriminant is 0. So what's the discriminant of this expression here? B squared 25 minus 4 times 1 times k equals 0. I want it to equal to 0 because I only want one solution. 25 minus 4k equals 0. So negative 4k equals negative 25. K equals 25 over 4. The magic number k that gives me only one solution is 25 over 4. And we have to know that one solution means your discriminant is equal to 0. If it's positive, I have two real solutions. If it's negative, I have two complex solutions. And when we say there's only one solution, there's one repeated root. It's a repeated solution in this case, when your discriminant is 0. Number 6, algebraically show that the system y equals x squared minus 4 and y equals negative x minus 5 has no real solutions. Well, when I solve a system, I can use substitution. So I'm going to pick up that negative x minus 5 and plug it in for y. Negative x minus 5 equals x squared minus 4. 0 equals x squared plus x plus 1, because when I solve a quadratic, I want it set equal to 0. What multiplies to 1 that adds to 1? Integers don't do that, so let's use the quad formula. A is 1, B is 1, C is 1. So we get x equals negative b plus or minus the square root of, we didn't compute the discriminant, we should do that. 1 squared minus 4 times 1 times 1. 1 minus 4 is negative 3. Negative 3 over 2. So x equals negative 1/2 plus or minus the square root of negative 3 over 2. Well, I know I have no real solutions because this is not a real number. This is x equals negative 1/2 plus or minus radical 3 over 2i. That is not a real number, so there are no real solutions. There are complex solutions, but there's no real solutions. If I graph these two, over here I graph these two functions, x squared minus 4 is a parabola that looks like that. Negative x minus 5 is a line that has a y-intercept of negative 5 and looks like that. If you check these graphically and type them into y1 and y2, you would see that they never intersect, which makes sense because if there's no real solutions, these two curves, these two functions, the graphs of their functions should not intersect. So algebraically, we ended up with complex solutions. To really solve the system, I would have to plug those back in, but that's weird. We don't solve systems with complex solutions. Graphically, we see that they don't intersect. Hopefully this lesson was a good review of the quadratic formula, and all we really added in were those complex solutions.